who got his PhD this summer from the statistical laboratory. After math, finance, and mathematics at Chicago, and prior to that, mathematical economics at Buenos Aires. Let me give you a very brief introduction to what we're doing. The goal that I set him is still a very long way off. So this is more mathematics. I think it's getting there. But the aim really was to try to understand the role, the proper role of new securities in covering previously uncovered risks. Take, for example, rates derivatives, which started off reducing risk and ended up producing risk. Similarly, 10 years later, credit derivatives, and so on and so on. I won't talk about options. Well, I will, but only as examples. So I learned something about backward stochastic differential equations. These were really started running in Paris. They're really a kind of French thing.
I think in Marseille.
In
Marseille, not Paris.
Ah, really?
Yeah.
Yeah. But Pardue and Peng's paper is the kind of key to getting it going.
They were in Marseille.
Ah, they were in Maastricht at the time. Okay, but they're still French mathematicians. Marseille. Sorry. Yeah. Okay, good. Well, it's a French thing then. Certainly taken up by Paris, as we all know. And indeed, around the world, for example, this week Peter Imkeller is speaking at Imperial College, looking at forward backward stochastic differential equations with regard to bond risk and things like that. And so this is a machinery that I think is really pretty important. Now, it has its limitations. We're going to do the very simplest cases, really. But we have results in Ezekiel's thesis that go beyond this, and we think we're pretty close to getting something that's a little more realistic. Ideally, what you want is to handle dynamic trading equilibria where there are a whole lot of forward cash flows. We haven't quite got there yet, but with a bit more work, I think we can manage that. So I'm first of all going to, but let me explain why we got into this. We spent up until about 15 months ago trying to work with the Pardue and Peng results in which the coefficients are Lipschitz continuous. This is reasonable. It's reasonable for individual agents, but you can't get the equilibrium that way. It just doesn't work. And so we decided to, why not just discretize everything and see what happens? And that works extremely well. So I'm going to set up, first of all, that's sort of introduction, the first two sections. And then the third one is just to set up essentially what a trader does from the point of view of optimal investment. And then we will look at the two problems that we're trying to address. The equilibrium pricing of new securities in an incomplete market to cover at least the risks of the current positions of the traders. And secondly, the design of the optimal securities, risk transfer, and so on. Results there are a little more limited, but we'll see that. And then I think something that Ezekiel did wonderfully well, took quite a bit of work, is to compute some examples. So I'll show you one most interesting picture that comes from quite serious computation, actually, even on a simple example, and then tell you where we hope to go, so to speak. So let's get started. So the motivation I more or less already said, but I mean the past 4 decades has seen the exponential growth of derivative markets. They're up to around mark-to-market value of 21 trillion. Now I would say that 3 trillion of that is actually just being listed annually from the outside world, but I spoke about that in the first talk I gave in September. And the notional value of 710 trillion at the end of last year. This is about 3 times global GDP. And the aim of this work in the long run is to produce a rigorous but realistic theory in which the risk reduction benefits of trading innovative financial products are realized and distributed amongst the market participants. So the toxic structured derivatives are not part of this game. We're trying to find out what's actually going on. So it has to be an incomplete market, and the traded new product should cover the risk previously unpriced. Now, the dynamic mathematical representation of the trader behavior must include their portfolio allocations, new and old, relative to their attitudes to risk embodied, and here we'll use risk measures, not utility functions, as is not quite standard in general equilibrium theory. Well, it's becoming in finance, but it isn't in economics, of course. It's the other way around, not the risk, but the utility. Roughly speaking, that's just a negative, multiplying by a negative sign, but of course there's a lot more mathematics behind it than that. So we have to get the dynamic trading equilibria, and these are dynamic, of course, over time, with the optimal design of new securities. So we're going to introduce a new theory of backward stochastic equations in discrete time. The theory is well known in continuous time, but it has all kinds of problems on defining and finding existence and uniqueness of solutions, depending on the sort of coefficient which drives these things. We'll see that in a minute. Okay, well, let me just pose the problems precisely. We'll assume we have n was a finite number of agents, n plus 1. You can think loosely of agent 0 as being a market maker, loosely. We're trying to sharpen that up a bit. When we were working in continuous time before we could get the equilibrium, we did quite a lot of work on this, but we just didn't have time to extend it to this framework so far anyway. It's an incomplete market, and there are m existing assets being traded in the market with an exogenous discounted price process, S. The equilibrium problem is we're given H new securities with payoff, C, and we'll find that we want a discounted price process, a typical equilibrium problem. We want to find the discounted price process U that clears the market. That's the constraint on the bottom. And also minimizes for each agent their risk measure. So the strategies, oh, I have a thing here, right? Let's see, what do I press? That one? No. Wait a minute, what's that? No, I don't seem to be able to make this work. Maybe I'm going the wrong way around, that's possible. Ah, there you go.
That's what I did.
That's a problem. Let's see. Now I'll mess this up terribly. I think I'll just go back with this. Oh God, I'm going the wrong way.
Yeah, that's
No,
right.
that's
Oh, sorry. There we are. Yeah.
So when you say H new securities, you mean that's the notional supply?
Well, H is no. That's a number of new securities I'm going to introduce. Yeah, yeah. And we're going to design them ultimately. But the point is, we're going to have H has to be at least one.
So that's a dimension of vector U.
That's the dimension of the vector U, exactly. Yeah. So there are going to be two trading strategies, of course, depending on the price changes. Trading the existing assets and trading the new assets. And that's the market clearing constraint. And the security design problem is the same as this, except now we also want to find a payoff vector for these new securities that minimizes the aggregate risk in the market across the agents. That's the idea. Okay, so let's look at backward stochastics difference equations. So we call these B as delta E's. And I mean, at first...
So what's your notation for difference equation?
Difference, yeah, it's discrete
differential.
time, that's the point. Yeah. And so we can think of this, I need to look at some notes here probably just to make sure I say the right thing. Oh, the other thing I should have said is that the first person to look at security design problems was a person that I knew, Karl Borch, who in a couple of papers in 1960 and 1962, I met him, of course, in Oxford in the mid-60s or late 60s, he looked at reinsurance design. And really, his ideas are still there in a sense. It's very, very forward-looking work. Okay, so backward stochastic differential equation works like this. We have a terminal condition, and then we have forward innovations, and a kind of, this is essentially a sort of forward dynamic function, which is called a coefficient. We're going to have here a fixed horizon. We have actually gone beyond that, and I'll maybe just say something about that at the right point. Now, Bob Elliott, who I was at Oxford with a million years ago when we were junior faculty, has recently done something like this with, but finite state. So it's basically just a Markov chain. And the other thing is that he gets uniqueness only up to some very complex equivalence relation, whereas of course we just get it, so to speak. So what are the questions? Well, existence and uniqueness. What coefficients? These are what drive a backward stochastic differential equation. We want to know what coefficients guarantee existence and uniqueness of the solution. We also want to be able to compare. Parameters are, of course, a terminal payoff and this coefficient function. If we have two of them, well, what conditions do we need on the BS delta E parameters to guarantee that the corresponding solutions are almost surely, one almost surely dominates the other? And then we have a usual, this is like a temporal continuity, which is termed a flow condition, which is simply if, suppose we have a time s less than our terminal time t, then will we have the same solution up to s as we have from 0 to t? From 0 to s, will it be the same solution? That is, so that's a question we want to have, and we want to say yes, of course, to that question. So we will work, and almost everyone does, with essentially a standard coefficients. These are vector valued functions, of course, and so we want to have that the map from y, which is is a state essentially of the equation at the current time. It essentially represents remaining risk to the horizon, is a bijection, and then everything will work out. And then we have a theorem that we have existence and uniqueness. So if we have a standard coefficient, then we have a unique solution, and the unique solution to our backward stochastic difference equation is either given explicitly, oh, I'm so sorry, I'm pressing the wrong button. Will this go back? Yes, it will. Yeah, we'll think about this like this. This shows you that this is essentially an innovation in the next period going closer to the horizon. And therefore, this is essentially, this is the state. We put that over to the other side, and you see it's absolutely explicitly given. And this is the implicit representation, like the backward stochastic difference equation or differential equation. And here it's discrete time, so it's difference. And you see that if y is independent of, sorry, if f is independent of y, the coefficient is independent of y, then that's also explicit. Now, this is the one proof I want to wave my hands at, actually. Which is, so we want to have this is our given difference equation. We assume this, and in a definition. And so if we take conditional expectations of this, and we use the fact of the bijection, then there exists, that means there will exist a yt. We're trying to find a yt that solves this thing. With that exists a yt that has that relationship. If we now equate our two expressions for yt, we will get this. And this, of course, is the implicit statement, and this is the explicit statement. So everything here is pretty straightforward. The one thing you should note, though, of course, that this is by definition curly ft measurable. That is measurable at t. Okay, now what about comparison? That's the next thing we want. Well, we say that, and this is the point that I already said, I think, in words. If for all, what we want is if this coefficient satisfies the comparison properties, if we have that almost surely y is less or equal y prime, then the corresponding relationship will, on the right-hand side, will be also an inequality. And also the other way around. Now, sorry for the n there, that's a slip, that should be just r to r because it's supposed to be the scalar case when f is just single dimension instead of a vector one. And then the comparison theorem, that's the comparison property, that's what we want, and the comparison theorem says that we can get this. Providing, of course, we have a standard coefficient. Now I'm going to wave my hands at the proof of that. Similarly, with the flow, all these things, I mean, are just pretty straightforward. So here's the flow condition. Now this is quite important because it gives us essentially uniqueness. So now we're using, I should have pointed out, we're now using this notation to say we'll go from the equation, we'll go from the backwards stochastic difference equation to the solution. That's the map we're trying to find. We know it exists and is unique. So let's suppose we have two of these. Then we have that these two things agree if t equals y prime and t equals z prime.
So
Again,
what gives you uniqueness is that you require that z is a martingale?
no, it has to have mean zero. Yeah, it is a martingale essentially with mean zero. Yeah, that's right. Conditional mean zero. Yeah, that's right. Yeah, that's correct. Okay, so now let's go to convex risk measures.
But what you call z is the martingale difference, right?
Essentially, yes. Yeah, that's right. Yeah. Okay, now convex risk measures. Well, of course, Hans has been speaking about these very elegantly for the last week or so. And so I'm just really running over this stuff. But we want to have, ideally, and we don't quite have this yet. We thought we had it, but we found an error which has to be patched. This is ideally what we want, and I'm going to tell you why. Well, it says down here, actually. Further on the slide. We want to have cache subadditive risk measure. Now, the idea is kind of interesting because, you know, for many years I ran with various people like Jim Merles, Joe Stiglitz, Michael Bacharach, John Enos, and so on, the Mathematical Economics Seminar at Oxford. And we trained an enormous number of people who've been presidential advisors in the US and governors of banks, of central banks and everything else. And in those days, in the 70s and 80s, you know, nobody wanted these things at all. All utility had to be, following really from the work of Ken Arrow, you know, utilities aren't additive. You have to do everything so they're incomparable, I should say correctly. However, in the field of finance, that's exactly what you do want. And so that, from the point of view of at least rather ancient mathematical economics, still important today. We were talking about Truman Bewley yesterday, actually, and Roy Radner and so on. You know, in those days, one tried to get away from the fact that you could add utilities. But here, that's exactly what you want because everything, the risk measures are all in cash terms. So it makes good sense. So first of all, they're decreasing, they're subadditive, which essentially means that if you add capital C, that decreases the risk measure by at least C. And then convexity, of course, I strongly agree with what Hans introduced. This should have come in the first place, in a sense, from my point of view, because it allows you to use convex analysis, which of course we're going to do, although I'll just wave my hands basically, but it's all straightforward if you know convex analysis. Okay, so a cache additive one, of course, it's an equality. But that isn't what you really want to do complex real problems. For example, if you're going to have multiple cache flows forward, which are the positions of the agents, which is realistic, then you're going to have to discount them. And as soon as you get the discount factor in there, you've got subadditivity. This has all been done by, well, I mean, it's been most recently studied at least by El-Karoui and her co-authors, particularly Pauline Barriou, who actually happened to be Ezekiel's external examiner and was very pleased with this work. So at least we've passed it before an expert, so to speak. Okay, now a dynamic convex risk measure maps time t payoff to an adapted process that satisfies all the usual stuff again. So this is what we're after as dynamic ones, because we want a dynamic trading equilibrium. And the main references there are again to El-Karoui and Barriou and so on. They're the ones who pointed out this cache, I believe, Hans can correct me if I'm wrong, that pointed out that this cache subadditivity is really important from a practical point of view, actually. And they worked the whole thing out for that. And I'm going to show you that here, but we can't get our equilibrium with it yet, quite. So we're going to use a backward stochastic delta difference equations to define dynamic risk measures in terms of coefficients. So if we let f be a standard coefficient and satisfy the comparison properties, also it's convex in y and z. Y is the state, z is the martingale innovation, if you like. It's decreasing in y. Then for any time t payoff x, that defines the map from the backward stochastic difference equation to the risk measure and the innovation is a cache subadditive risk measure. And actually, you can normalize it. And if it, of course, f doesn't depend on y as we observed before, then it's cache additive, not cache subadditive. Well, this is again just grinding through this basically, and it's not worth looking at. It's just all pretty straightforward. First of all, monotonicity, time consistency, normalization, convexity, cache subadditivity. Everything here is pretty mechanical. It's not really deep. Once you put it in this framework, you just knock it out, basically. It's not anything that strains the mind too much. Okay, now what about, sorry.
In the continuous time case, there's...
continuous time is a different...
Yeah, but I'm just asking the question. So in the continuous time case, there is a result of pain, which says that basically if you start from a time consistent to dynamic risk measure plus some Lipschitz condition, then it's always representable as a backward stochastic differential.
That is correct, yes.
Is there anything similar here? I guess it should be even more general.
Yeah, this is the same kind of thing, actually, I
And
think.
you can always write it.
Yeah, that's right. Yeah, that's basically what we're proving here. Yeah, that's right.
But you prove it one way.
Yeah, just one way. We're not doing forward, backward. Well, at least we haven't looked at that. Now, this is what typically, and again, Hans introduced this a couple of lectures ago, I think. This is what people normally use, an entropic risk measure, which basically is based on an exponential utility, essentially. It's not state dependent, so the y is gone. And more generally, however, we can have a collection. So this is useful to get results. And more generally, we can be given a collection of static convex risk measures. Excuse me. And then we can generate a dynamic convex risk measure with this coefficient like this. Let's see. Whoops, that's what I want. Now, let's try and apply this to a financial market. So that's the sort of machinery we need. Let me just see where I've got to here. One thing I should have pointed out, that, I mean, I found this extremely confusing in both reading papers and actually trying to do some work, but I should go back one slide. Let's see if I can get back there. Yeah. I mean, somehow you play fast and loose with negative signs, and you have to understand intuitively what the heck it means. So here, the minus in this innovation, in defining the coefficient from the risk measure, is coming about because of the signing, which I still find rather non-intuitive, in backwards stochastic differential equations and backwards stochastic, therefore, difference equations. So I just thought I should point that out, because if you're puzzled, you have to actually think through it to see why. Okay, so now let's look at this, let's apply this to a financial market model. So we're going to look at a standard trading equilibrium. I was a pupil at one point of Herb Simon, and he used to say, I don't know why often they waste all this time, you know, trying to study a full equilibrium, a la Arrow-Debreu or whatever, you know, with production and everything. And it's because he said, well, that's a Carnegie Mellon view, of course, anti-Chicago. It isn't realistic at all. He said, what if they just stick to trading equilibria? That's something you know is real and you can actually handle it. And that's, of course, what we're doing here. So we have M assets. These are the ones that we're going to be given. They have a price process given, ST. There's no arbitrage, so we have a set of equivalent martingale measures because it's incomplete. There's completeness if and only if, of course, there's a unique martingale measure. And we're certainly not assuming a finite state model. So one of the things we're going to be interested in is the trading gains of a self-financing portfolio. So notice we're going to express our excuse me. This notation is not very good, but you see, this is a drift of the price. This is initial condition. This is a drift, and this is a volatility, which is a martingale, mean zero. Okay, so we're going to look at those trading gains. So this is the strategy of a single trader we're interested in. So we're going to try and minimize this over all acceptable strategies. Now this can be pretty general. In fact, there have been some very recent papers, more recent than this work, I think, in a sense, where people are using non-convex acceptable sets. But most of the literature has some kind of, that is a convex set of paths. You know, like, for example, no short selling or limits on short selling or whatever. I mean, it's all going to be some kind of cone or box or something. Okay, so, but for us, it's just general. So what's the total risk given by the backward stochastic difference equation? There it is, that's the total risk. But we can redo that into the remaining total risk by adding the gains to trading a self-financing portfolio up to T, right? So these are the gains up to T. And then we can express that like this in terms of the backward stochastic differential equation. So now, so this is the remaining total risk for a given, excuse me, for the whole system. And so now what we want to do is use the comparison theorem to find the minimal risk by minimizing this. This is for an individual. So here we've used some results of Barrio and El-Kharoui. And they've shown that if the coefficient is standard, we can define this as an essential infimum. And if we do that, then this so-called market-modified risk measure, if the coefficient is standard, convex, and satisfies the comparison property, then the optimal residual risk is given by that backward stochastic differential equation, and the optimal strategy is given. There exists an optimal strategy, and the coefficient, this market-corrected coefficient, is this, and that's over whatever the constraints are. So now, and this is the problem that we struggle with for some time, trying to do it in continuous time. We can do it in continuous time if, in fact, the new securities cover all the risks in the system, as opposed to the risks that are in the agent's positions, in their endowed positions. I think we're going to write a separate paper on that because it's quite neat, and again, it's quite mechanical. Okay, so we're going to try to address the problem of finding an equilibrium price for an arbitrary set of new securities to be traded among a set of economic agents, where each agent at the moment can partially hedge their risk by trading in the market of existing assets, but that won't cover their positions, the risks of their positions. So we want to design securities, ultimately, that will do that. So there are n+1 agents. Each one has their risk measure and their market modified risk measure, which is defined, denoted by this coefficient. There are m existing assets, and we're going to introduce h new securities with a payoff vector xi for the moment given, but then we're going to try and find the right one, so to speak. So we'll find, what's our problem? We want to find a typical equilibrium problem. We want to find a discounted price process, so that for each of the agents, they are actually minimizing their market modified risk measure, and the market clears. So, since we're in discrete time, it's blindingly obvious once you see it, but it took us a while to see this. In the discrete time, actually all you have to do is do it for one period. So that's the local in time problem, and then you can do a backwards iteration and get the whole dynamic equilibrium. So first of all, we'll just look at one period. Now, actually that's a mistake. It's 2013. And it appeared after we got these results, well, as I'm showing you. So this is independent. Patrick Cheredito and co-authors got, sort of similar results. He uses utility. He uses some of the same examples when he gets some stronger things, which we also had, but we didn't consider as a full theory and so on. We actually presented, or rather Ezekiel presented this at the Cambridge-Princeton workshop here in September. Patrick was very impressed with it. We had a long discussion with him, and so I think we've run it out in front of the experts anyway. But his approach, I mean, it's not, in terms of backward stochastic difference equations, although he also uses that term in the paper for a special case. So we assume that for each agent, the coefficient governing the appropriate backward stochastic differential equation for their risk measure is a convex risk measure. It's continuous from below. This is again a condition of Barrio and El Khoury, which basically says that as the risks go up, minus the coefficient again, minus the risks go down. The coefficient goes down. So again, that's this playing with signs that's slightly confusing, but when you think about it a little, it works out. So the local in time equilibrium problem, we're given positions and a volatility of the new securities. So what we want to do is design the new securities so they're going to have a drift and they have the volatility in it's a standard kind of evolution equation. And we want to clear the market. And we know that essentially we're going to have an essential infimum over the possible strategies. Now this is for all agents. But so we're going to define this for a given agent. And then we're going to apply convex analysis. We're first of all going to take a convex conjugate. Then we're going to take an inf convolution. And we have the following theorem. We have to assume that the inf convolution is finite, that 0 belongs to the interior of the domain. That's a regularity condition standard in any kind of abstract optimization. And that the inf convolution is actually attained. Then it turns out that, and this is again standard from convex analysis, that the drift coefficient is a member of the subdifferential of this G function at this inf convolution at 0. And so we have this. That is to say that these strategies solve the local equilibrium problem. And then, I mean, it's just standard analysis from Rockefeller's pioneering book to get the result. So now we'll have for the whole market, we will have these BS delta E coefficients. And there it is in vector form. We have terminal positions and we have payoffs at this point specified for the new securities. So we can solve, and this is what we couldn't do in continuous time. The equilibrium problem from this BS delta E to the solutions, which are the price solutions and the innovation. So these are the optimal strategies. This is the equilibrium drift. These are the optimal residual risks. And U is the equilibrium price for the securities with this drift and this volatility process. Yeah, sorry.
So uniqueness is a very special thing in general equilibrium models.
Yeah.
Is it the sub-additivity that's the key assumption here?
Yeah, I think so, yes. Yeah. Well, additivity we have, and everything's convex, yes, that's right. That's right. And that's where...
Within complete markets, so additivity isn't, well, it depends on how you set it up.
Yeah, well, it certainly works.
So in some models of incomplete markets, like I think of hard stuff from a long time ago.
Yeah.
The spanning is endogenous because it depends on the price. So there are these funny non-uniqueness results. Now that's an maybe it's the discrete states.
I think that's discrete state,
Is
isn't
that
it?
important?
Yeah,
Maybe that's important.
that's important.
But, yeah, so what happens is that you have two different claims, and if they're traded separately, then they're spanning both sets of states, of all the states. And if you assume that that's true, then you find the price is the one that makes it so that the two are redundant. And so there's no equilibrium, because when the two are redundant, markets aren't complete.
Yeah,
You get a different equilibrium, so.
yeah.
So,
I don't know, I'd have to look, I mean, honestly, that was what our seminar spent an enormous amount of time on all that stuff. But it's so long ago, I haven't actually gone back to it. Your memory on this is much
I
better
don't
than
know.
mine.
yeah, I don't know, I've always been intrigued by that paper, but part of it depends on how you define security.
Which paper we're talking about?
This is Oliver Hart's paper.
Ah, Hart's paper, yeah,
The
yeah.
one
Yeah, yeah.
where you have these two securities, which if you assume that they're priced so they aren't redundant,
Yeah.
then you get an equilibrium that comes out with a price that implies that they're redundant. If you assume that they are redundant, then it's the price that comes out is one that makes
I should
them
have a look at that again.
not redundant.
Didn't that appear in the Review of Economic Studies?
Probably, I don't remember.
I think I
I'm
might
not
even
that
have
good.
handled it.
I'm not that good at things. It was a clever little paper. Now, some of the
Yeah.
examples,
It's certainly in our references and also in Patrick Gerardito's references. Yeah.
yeah, so I don't know, I'm just trying to figure out what's going on in your assumptions to rule out these things.
Well, I'm pretty sure that, I mean, you know, it is certainly, there's lots of convexity floating around, that helps.
Well, they have
So,
convexity too.
Yeah,
I have a different question. So, the way you introduce these new securities,
Yeah.
it's always going to improve the situation, right?
correct,
Because you just optimize
Correct.
over a larger space.
That's
Same
correct.
thing.
That's right, yeah. That's the idea, of course, basically.
Yeah, but another way to see financial innovation is, I mean, when you have new types of financial
Because that would take 3 trillion from the world economy, yeah, that's another way to see them, for sure.
Even without going into this consideration, so I introduce a new type of security.
Yeah.
So I'm a JP Morgan's
Yeah.
structured products guy,
Yeah.
and I understand exactly what's going on with the security, but most people don't really
Exactly.
understand it. So they look at the risk, they say, oh, you know, this is a new, I can diversify my portfolio, I solve these optimization problems, I can reduce my risk, so I invest in this new security.
Yeah,
And so there is a bubble where you have a lot of investment in this new security, and exposed, actually, because of these flows of funds, because of these transfers, because I have to sell, I have to invest less in something else to invest in this new security. So I'm exposed.
well, I think we're covering that in the model that we've got here, because, you know, we're trading in the existing securities and the new securities, and obviously the money's got to come from somewhere, you're right, I mean, in a sense.
Yeah, but the risk measure, is it based on, I mean, let me give a simple example, not even derivatives. Let's say I introduce a new kind of investment opportunity, which is called subprime. Nobody understands really what this is.
Yeah.
And then I market these people.
Yeah,
get
well, I
marketing
mean,
presentation.
this is a real world phenomenon, and as I began in my introduction, that is not what we're trying to model. We're trying to model, as it were, where there is genuine risk reduction, and I am in a minute,
Yeah,
literally,
but
going to
there
show you an
is-
example where that
There is genuine
quite
risk
neat.
reduction because when you introduce it, people look at the correlations between this new asset class and
Yeah.
their old stuff, and they
Yeah.
see negative correlations or zero. So they see genuine
Yeah.
diversification
Yeah.
opportunities. But then due to the fact that it's, you know, the money has to come out of somewhere, they disinvest from something, they
Yeah.
buy into this new one. So there's an endogenous price process which emerges, and exposed, it's not uncorrelated. It's not uncorrelated because now we have portfolios with both of them, and when you have to disinvest from
Yeah,
something,
I see your point. I see your point.
and this is real because if you look at the subprime example, I mean, there's
Yeah.
But there's this empirical study by
I
Ross.
recognize it as a real-world phenomenon. I don't quite see how to deal with it, and whether we've dealt with that in this model or not. Off the top of my head, I think we have, but maybe not.
Or another way to think of the new introduction of financial innovation is an analogy with the species, like when you introduce a new species in an ecological
Yeah.
system.
Yeah, sure.
If you look at the
Yeah.
Australian
Absolutely.
example, they introduced these
Yeah.
rabbits in Australia. There were no rabbits in Australia.
Yeah.
It's an extreme example of
Yeah, absolutely.
But then they overran the whole country because there was no balancing mechanism.
Indeed.
And so this is, I think, when I think of financial innovation, I think of this example, invasive species. Whereas this way of introducing it is a tame way. You will always get a nice reduction in risk. So I don't see where that phenomenon comes out or what excludes it.
So I'm confused.
Well, I think, I mean, I'm just responding to the question. I see what you're saying. I think that is the real situation. What I don't see clearly in my head at this point is whether or not that's covered here. I think the answer is not, because I think that comes because we've got a new product. We're going to make a lot of money from the product. We misprice the product so that the risks covered relative to the price paid is not appropriate. Certainly that's what we've been doing in the, I talked about in my talk in September. I mean, that's just a fact. And I estimate it to be 3 trillion worth of fact. So it is, I think, a bad thing. But here, what we're trying to do is just see a structure in which, if new securities come in to cover the positions of the current traders, that they will be better off with or without a market maker, although I'm not going to speak about that today, or market makers. But I agree with you. That is the thing that actually was driving us to try and do this. For example, and we tried to do this in the continuous time, basically there's a market maker. The market maker actually introduces this new security. So is it going to be what we've got here, or is it going to be something that is actually a bit nastier and, causes a bubble, as you were saying? And I think that it could be that case, but we haven't really tackled that. On the other hand, that was exactly that kind of problem, was why we got into it, at least from my point of view as a supervisor.
So this is a very strong result, because in most of these competitive models, if you add additional trading opportunities, the price effects can clobber you. And so you can't necessarily say that people are going to be better off if you add securities. Often,
Yeah.
you add. There's some kind of whiskey in the U.S. that I like, and you add trade in the whiskey, and all of a sudden the price goes way up, and I'm worse off because that's important in my consumption bundle.
Yeah.
Or you have something in my endowment which is kind of expensive now, but if the prices were more correct, which they will be when you add more securities, it's going to be cheap, and all of a sudden my wealth is pretty low, and now my downside risk is going to be bigger. And I'm surprised, there has to be something very strong in the assumptions to rule out this kind of.
Well, this is very useful discussion because, I've got to look carefully at this as we're in the middle of writing this up now. Those questions have to be addressed. There's no question of it at all, but I honestly, off the top of my head. However, let me show you in the last 10 minutes.
What you do have. Okay,
Yeah.
yeah.
The example. Okay, so, oops, what am I doing? Wrong one. Here we go. Okay. Okay, so we've got this equilibrium. Now let's go to exactly what we're talking about now. Let's suppose what we want to do is characterize in this context the introduction of new securities that cover previously unpriced risks that minimize the aggregate risk of the agents. So we have individual risks for arbitrary securities, see, and now we're now going to try and find that payoff that does the job. That's the idea. Not with not, I believe, with the phenomena we've just been discussing. So we can write the aggregate risk for the arbitrary securities. Again, we're now using just a notation going from the backwards stochastic difference equation to the solution for this given C. That will give us, you know, the usual stuff. We're here now looking at, you know, we want to look at this trading, and we now know how to do all this. And so the minimal possible risk is given if we go to this market-corrected coefficient introduced before, that's due to El-Karouian value. This is given by this inf convolution, and we assume it's attained, and then there exists the appropriate drift, and so on and so on. So it's all just applying the machinery we had before. So in order to create the optimal securities, we need to solve this system. This is the notation for the backward stochastic differential equation to get its components. And here's the theorem that does that. And then this is an equilibrium drift. This is an equilibrium innovation, and for the equilibrium price. Well, again, it's just, you know, grinding out mechanically, essentially, the result. Okay, now let's look at an example in the closing 5 or 10 minutes, because I think this is one of the strong contributions of Ezekiel to this. I'm going to flip through the slides here to get to what I want. Now, what I should have pointed out that all we're doing, we're not completing the market in the sense that there are still, you know, there's still some, in the innovations of things, there are still things that are not being priced. What we're doing, though, is we are reducing the risks of the positions of the agents. That has to be stressed. So, sorry, let me just. Yeah. Okay. So how do we solve these types of problems? Let's do a simple thing. We've got a simple, you know, one-dimensional state process, and paths are in a recombining trinomial tree. We've got probabilities for up and down, as usual in a trinomial tree, and the filtration will be just generated by this tree-type process. And of course, as t goes to infinity, our horizon, this converges to a log normal
Well,
process.
in what sense? I mean, spanning is changing in things.
Yeah, true. No, we don't really need that. It's just an
Okay.
observation. Yeah.
Okay.
No, we're going to fix our. I said we're going to fix our horizon.
Okay.
Okay, we're going to have entropic risk measures, and here's the situation. I know. I've dropped from. How do we solve these things? Well, it's essentially using a Longstaff-Schwartz backwards type recursion, and actually then it's critically important, as always in those things, what you use as basis functions for the regressions to do the backward. And there's been very nice work by Bender and Steiner 2 years ago, I guess, using martingale basis functions, which are really quite neat. And that's what we used computationally. Okay, so here's the situation, which I think is informative. So we've got one agent whose position is bad and, you know, around, as it were, you think about it as the, you know, as a strike, let's say at 100. His positions look pretty good except there. Then we've got another person who looks terrible unless he's around the strike, okay? So we want to see if we can design a security where both of these guys are made better off. The initial risks, I mean, this is just the numerics of their positions with this payoff, the underlying process, are 2.52 and 0.642. B is obviously better off, the red guy, because he's mostly over this range of this price process. He's winning rather than losing. He only loses when it goes around this 100.
So is this a one-period example, basically?
Yeah, essentially. No,
Is it
that's not a one period,
Is
no,
it
it's,
pay- so
no,
that-
it's
is that the
it's a
terminal
process.
payoff?
This is the terminal payoff, yeah.
And so, but are the two agents' payoffs a function of the terminal payoff?
These are the two agents' terminal payoffs, their
Okay, so-
positions at the moment.
So they're the function of the state variable at the end,
Yeah.
not a function of the path.
Yeah, that's true, of course, yeah, that's true. Yeah.
That's what I mean by one period.
Oh, sorry, yes, in that sense it is, yeah. Okay, now, however, I think it's still informative.
Okay. I'm not saying it isn't, I'm just.
Okay. Okay, so we're going to introduce an arbitrary security. First of all, let's just try an arbitrary security. Let's just look at a call option where around this at the money point 100, the middle, the expectation process. Okay, so what are the risks if we introduce this new security and it's traded? The answer is that it's been reduced. With our B guy who was pretty well off to start with, he in fact gets a gain. This is the market maker, obviously. So that isn't too bad. But let's see the optimal security. There's the optimal security. So, and you can see by the diagram that it's relatively straightforward to construct this as
What's the difference of the two?
well, you can do it, yeah, I mean, you can do it with call and put options. So the thing we introduced before, we just put it together, right? Now, the point about this is that of course, this is the position, this should be long, that's our agent B, and this should be short, that's our agent A. And you can see that that improves the positions we had before for both guys, both for A, the red guy, and blue, the B guy, are color coding isn't too good there, but you see the idea. And then the risks with the optimal security. Now, the guy who was quite well off, the B guy in the first place, his risk is he's got an even bigger gain, and the other guy's risk has been reduced from, well, I've got a table here in the next. There are the initial risks with no securities. There's with just introducing a call option. If we introduce calls and puts and then construct that security, then this guy is agent, oops, I'm so sorry. Agent B is actually getting even more, not an awful lot more, but the total risk has gone down a lot. So this is just a little example to show the idea, and it doesn't answer the questions that we were worried about, but I'll have to think about those. So let me just conclude where we are now. So where agents have cache additive risk measures, we've characterized dynamic trading equilibria in discrete time and incomplete markets. In the continuous time cases I've mentioned, when the new securities complete the market, cover all the risks as introduced in the model, then we have similar results using BSDEs. Because in that case, when the market completes, then the BSDE, the continuous time BSDE that expresses everything equivalent to our discrete time here, actually is Lipschitz continuous, and so you have existence of uniqueness. Now, we've also done payoff streams. We've established random payoff times as opposed to a fixed horizon. It's more complicated. It's just more machinery, basically. It's essentially the same ideas, but that can be done. We would like, however, to get the cache subadditive one, which we haven't quite got. We're nearly there, but I think we're there. We're nearly there anyway. And just to conclude, these BS delta E's, this theory is perfectly straightforward. It's not deep. And it provides a convenient framework for solving these problems in discrete time, which in reality is good enough, I think. And then What we want to do in future, though, is study the problem of optimal securitization from the point of view of a market maker. In a sense, that little example shows you that, one guy kind of looks like a market maker there. He's taking the risk just around a given part of the price process. Then the design of optimal securities. I just showed you one where H is fixed a priori so that the new securities don't necessarily complete the market. And then the generalization of the solution to the equilibrium problem to cash subadditive risk measures and payoff streams with random payoff times. We've got the beginning of that. We also have, a la Musiela and Zarafofalou, series of papers, 2008, 9, 10, the horizon independent strategy. This is a kind of robust strategy. I mean, it's quite strong, this horizon independent stuff. But it's very nice because most problems, particularly for large asset managers and so on, there isn't really a horizon. Horizon is somehow imposed. So it's rather, but the problem is that what you pay for that, I think it's really interesting work which hasn't been developed enough. Marek is too busy trying to raise money for the Mann Institute at Oxford, he claims. But I mean, it is interesting work, but these strategies are much more robust than one which allows, more flexibility and depends on a terminal date. But that, I think, makes sense. And that's actually in Ezekiel's thesis, too. So I think I've used my hour. Thank you very much. I think you see Hans there somewhere. I think, yeah. Yes, there we are. So, further questions, comments? Okay, thanks very much.